All right. So, yeah, I thought about what to talk about for this presentation. There's actually some work on more sophisticated benchmarking methods for my group that Carl Perch will be presenting on. So I figured I would do something a little different from my part. I wanted to start by telling you about a class of optimization algorithms called minorized maximization algorithms. Expectation maximization is actually a special case of these methods. The idea is that, let's say you have a very complex optimization landscape, and you have a particular point in that landscape, the yellow dot where you're currently located. If you want to reach the maximum of this function, what you can do if the original function is too hard to optimize is you fit some kind of surrogate function that is equal to the target function's value at the current location and lies entirely underneath it, so it's a lower bound. And then you optimize that lower bound, you get to some new location, fit a new surrogate function, and then proceed like this. This is not actually an algorithm so much as a framework for creating optimization algorithms. Expectation maximization, all sorts of variational methods are basically special cases of this. So the mathematical formulation is if you want to maximize f of x and you're at some point xn, then you construct a surrogate gn of x that is a lower bound and it's equal to the function value at the current point xn. And then you maximize gn instead. And you might want to do this for all sorts of reasons. Maybe these surrogate functions are easier to optimize, things like that. Now, this is not a talk about optimization, it's a talk about benchmarking. So some of you might have already guessed where I'm going with this. But when we're doing benchmarking in robotics, what we really want is something that's completely unattainable. We want to know how well our method will enable robots to take over the world or something like that. Whatever your view of the ultimate robotics objective function is, it's not something that's very easy for us to measure. And when we're doing benchmarking, what we're doing is fitting surrogate functions that are much more practical to optimize and hopefully have something to do with the value of the actual function that we're after. All right. So this complicated function is how well our robot does in the real world with your method. And your benchmark is the surrogate function. And there are a few conclusions we can draw from this analogy. For example, one conclusion is that benchmarks are local, and it is okay if your benchmark is no longer relevant some number of years from now, maybe some number of months from now. In the case where you're setting up a benchmark for just your paper, it might not be relevant some number of hours after the paper is published. That's not necessarily a bad thing, as long as you can make some progress on that surrogate function, and it is, in fact, a lower bound to the true objective and satisfies a whole bunch of other unreasonable criteria, it can actually be a good thing. And I think it's very important for us to keep this in mind when we're thinking about evaluation in robotics, that really the goal of evaluation is to drive progress, to get to that peak, and everything else kind of follows from that. So you can make all sorts of mistakes, like for example, you can construct your surrogate function so that this property, the lower bound property, is false, and then you can optimize the heck out of your benchmark and get a really, really terrible method, so that's no good. So if not constructed very carefully, benchmarks eventually become misleading, and we all kind of know that, and the math tells us that, I guess. But the thing that I want to emphasize is that these problems, the locality, the fact that your benchmark will become irrelevant, all that, these are just not things you can avoid. And what we should be doing as a robotics community is learning to deal with this stuff and not being too hard on ourselves when we don't quite get this right. So I want to tell you about some benchmarks in this framework. Now, I spend a lot of my time as a machine learning researcher working on reinforcement learning algorithms, which I know is a topic that is justifiably much maligned in the robotics world sometimes for all of its quirks. But it's also a world that has experienced a lot of interesting ups and downs when it comes to benchmarks. Some of you might be familiar with the OpenAI GYM benchmark. This has been a very popular thing in the reinforcement learning community, created circa 2016, so about 9 years ago, based on some Mujoko tasks that were carelessly ad hoc constructed by a bunch of people that didn't know they were making benchmarks at the time. And it looks kind of like this, so it's a little bit silly. You get these humanoids that kind of try to walk, but instead end up writhing on the ground. So it's kind of lame, and it has led to enormous progress. In terms of the amount of progress that we've made on reinforcement learning algorithms, this benchmark has enabled it far more than cart pole or whatever, or any of these other popular things. So there's kind of something there, even though there's also a lot of ridiculous stuff. So why has it led to such huge progress? My claim here is that it has to do with this property, that at the time, 2016, when this was constructed, it was the right thing at the right time that captured a good kind of proxy to the relevance of these methods for real problems. The real problems, that these are the fruits of that we're harvesting today in the form of, for example, sim-to-real algorithms that are very widely used in robotics and increasingly used in practical robotic applications. And in 2016, this kind of stuff was what allowed Gn of xn to be equal to f of xn, meaning that it allowed the measurement of the performance of those algorithms to be reflective of the soon-to-be practical utility of those algorithms. And this benchmark is not very helpful anymore. Why? Well, because the axis along which we can optimize our methods with this benchmark, it's kind of basically there. Like if you want to put a simulated humanoid, if you want to simulate a humanoid and optimize a policy for it, like that kind of works. And you can eke out the last like little bit of performance, but there are much bigger challenges to contend with in this world, in the world of reinforcement learning methods like generalization, handling complex variability in the physical world, perception, all this other kind of stuff that these benchmarks did not do a good job of emphasizing, meaning that at this point, the lower bound thingy is really hitting you, where now you're kind of at the peak of what you can get in these things, and getting that last little epsilon isn't actually getting you the last little epsilon for real world performance. So viewed in this way, this was actually a very, very good surrogate function. It lasted for quite a number of years, and it led to huge progress. And for all of the negative things we can say about it, it was good. D4RL, this maybe is a little bit less well known, but in the world of offline reinforcement learning, this is a benchmark for measuring progress on offline RL methods. It was very useful at the time. Why? Because at the time, progress on offline RL methods was being measured on tasks where imitation learning methods were actually really, really good. So unintentionally, progress on offline RL meant making them more like imitation learning, which is not really where they shine. So what D4RL did is provide a bunch of tasks that emphasize putting together different suboptimal pieces into a longer, more optimal trajectory. So in this case, a navigation task, for example, where you see a lot of navigation from A to B between different points, and you want to synthesize a policy for navigating between two different points where you do not see an optimal path in the data. So that exercised a particular dimension of these algorithms that was weak at the time, and has since become much, much stronger. So again, this task is even more lame. It led to really huge progress. Offline RL methods become a lot stronger. And it's also not helpful anymore because that dimension of weakness in the methods has been addressed, and we need to test and exercise other aspects of the problem. So that's kind of the global philosophy, but let me zoom in a little bit more into things that are maybe more relevant for us as roboticists. So right now, in robotics, generally, if you're a robotics researcher and you want to run real-world experiments, which is a very good thing to do, you should definitely do that, everyone's going to set up their own tasks and run their own comparisons because we don't have much in the way of alternatives. And it's very easy to be annoyed by this because if everyone is setting up their tasks, you might say that nobody's really comparing to anybody else, but it's not so bad. So it's still a surrogate function, it's just a very local one. Like who says that that surrogate function for the benchmark needs to actually extend to other researchers? If you can use it to draw a vector in the direction of better algorithms, develop better algorithms, and then like write about them in a paper that everybody else can use, that's a good thing. It does, however, require more honesty on the part of the researchers because you have to like do all the comparisons. But this is important to realize that requiring honesty is not the same as being bad. Like it's good to be honest. And on the plus side, there's actually a silver lining to this stuff, which is we can move fast in terms of creating new tasks, setups, and robots. If everyone is going to set up a different task, then essentially the task and the robot and the problem is going to evolve more rapidly because there's more variability. And that's maybe the darker side of things like OpenAI Gym because, yeah, it really enabled a lot of algorithm progress, but it also resulted in a degree of stagnation if people take it too seriously and iterate on the same boring problem that we were iterating on 9 years ago. So benchmarking in robotics is really hard, and everyone has a different setup. Getting broad enough generalization from learned models on robots, and these days I think if you're making a lot of progress in robotics, chances are there's some kind of learned model somewhere. Getting a model that will run on someone else's robot is a big open problem. That's not something that's very easy to achieve. And the result is this kind of balkanization of evaluations. Again, not necessarily a bad thing. The good thing about it is it's very easy to develop a state-of-the-art method because no one else's model will work on your robot. And if you retrain someone else's model, it's going to be a little bit better, but it's never going to be quite as good. But the bad is that it's very hard to figure out which method is better. So you have to kind of keep yourself honest and make sure that you set things up. But yeah, it's not that bad. It's just a very local surrogate function. And I think that in the long run, to be practical, we really do need to allow every researcher to run their own eval. I think that there's more we could do in terms of standardization and so on, but I think if we're talking about real-world evals, I don't think we'll ever be able to get it to the point where it's like as perfect as OpenAI Gym, nor do I think we necessarily want to, because as roboticists, we want to be able to make progress on designing cooler tasks, cooler robots, and more interesting setups. So maybe we kind of want to keep that silver lining. And this means that all evaluations are at some level going to look like A/B comparisons. That they're not going to look like here's they're not going to look like ImageNet, where there's kind of a leaderboard of standard numbers and you just compare those numbers. It's going to have to look a little bit more like a comparison on your setup, and you can do more to make your setup fair and honest and all that other kind of stuff. And I will talk about that a little bit, but maybe accept that it'll not be the same as someone else's setup. Okay, so that's maybe a little bit of philosophy, but I want to get into something a little bit more practical and a little bit more close to my heart, which is a way that we could actually run models, learn models at least, built by other people on our own robots, and how that can facilitate better evaluation and benchmarking, at least for robotic learning methods. So these days, if you want to get a particular task to work with robotic learning, you get some data of that task on your robot, and you learn a model, let's call it Model A, and then Model A will hopefully do something sensible on your robot. And then if someone else has a different robot, maybe if I have a different robot, I'll collect data on my robot and I'll train Model B and it will work on my robot. And someone else will train Model C and Model D and so on. So if we take all the data that we've collected from all of our robots and we train one model on it, and then we run that model on all of our robots, in some ways it's kind of similar because we're still testing our own tasks, but now we're testing them with one model. And if we share those data sets and we can have one data set we're all training on, then we haven't fully solved the challenge of evaluation, but we've reduced one particular axis of variability, which is that little bit where we all can collect kind of weird data and we can't run each other's models. So as long as you trained your model on this cross-embodiment data set, then I can run your model on my robot. So that's the principle. And there's been some pretty considerable progress in the world of cross-embodiment robotic learning. So I think this idea was definitely not introduced, but perhaps popularized in this paper called RTX, which was led by Quan Wong and Carl Perch. Carl's actually speaking in this workshop later. Where what we did is we contacted a bunch of different robotics labs, about 33 other labs, and we asked them to donate their data to science, to contribute the data from their robotic manipulation system to a shared cross-embodiment data set that we could use to test out some of these ideas. I could tell you a lot about the stats of this data set, but maybe it's easier to just show you, like these are some of the videos from the data set that was collected. You can see that they're all robotic arms that are doing relatively simple kind of researchy tasks, but they are highly varied. They're doing lots of tasks, lots of different viewpoints. So a lot of complexity and variability there. One of the cool things about this cross-embodiment learning experiment was that it showed that generalist models trained on data from many different robots could actually do better than specialized models trained on just one of the embodiments. Now, here, of course, evaluation was a big challenge, and we had to rely on the kindness of the project participants to run a lot of evals themselves. So what we did is we took the cross-embodiment model and we sent it back to a subset of the labs that contributed data that were willing to run some evaluations. These are some of the tasks that they performed. And we simply asked them to compare the cross-embodiment model to whatever model they were developing on their own data. So each lab collected that data for a reason because they wanted to develop some method. It was a different method for each lab, and we just said, like, whatever you're developing, compare that to the cross-embodiment model. So in each group, the left bar is the model at that lab. The rightmost rainbow-colored bar is this cross-embodiment model. The middle one is a baseline for a different model. But on average, the cross-embodiment model did about 50% better than the specialized system that each lab was building. Of course, there's variability between the different labs. Some had a really great method. In some cases, the cross-embodiment model helped more. If they had very little data, you would have expected to see more transfer from cross-embodiment. But a 50% improvement in success rate on average for a model that was trained by people that never touched those robots really was actually pretty remarkable in my opinion. And this showed that actually cross-embodiment learning is something that we can do. We have recipes that can make it work, and it has a lot of potential. More recently, at Physical Intelligence, we trained a vision language action model on many different embodiments, many of which we collected data from ourselves, but we also included the open source data from this project that I mentioned before. And this model could do quite a few things. You could run it in zero shot to perform various tasks. You could specialize it by fine tuning. You could get it to perform very intricate tasks like folding laundry. And this is a model that will run on static bimanual robots, single-arm robots, mobile robots, all sorts of different platforms. So this is a mobile robot that's going to be taking laundry out of the dryer. So these things really work. They can control many different robots, and they can use very heterogeneous data sets. And we could also fine-tune these things to other robots. So this is the Pi0 model that was trained, as I mentioned before, and then it was fine-tuned to this humanoid robot from a company called Astrobots. And they collected some data for making coffee. They sent the data to physical intelligence, and we fine-tuned exactly that same Pi0 model to control this new robot to make the coffee. And it actually does it. Like it will use the coffee machine. It'll mostly do it correctly. Occasionally it'll mess up in various ways, but definitely something that is operating as expected. And this is another video. This is from a company called HEIBot that is also running a fine-tuned, this is actually a multitask fine-tuned version of a slightly more advanced Pi0 model. So it's putting on the scarf, it's going to be doing other things. It has some tasks where it's taking out trash bags and handing off menus at a restaurant, that sort of thing. Okay, so the current practical cross-embodiment pipeline, if you actually want to take a model that is trained on a public data set like OXE and adapt it to your system, is to collect a little bit of data from your particular robotic setup, because unless you actually contributed data to OXE, it's probably not actually in that cross-embodiment data set, so you probably want to fine-tune the cross-embodiment model and then run it on your target embodiment. And that's pretty good. That's what was done in those videos with the humanoids. But ideally, we would run on target embodiments in zero shot. So ideally, we'd be able to train this model and you could just test it on your robot. The technology is not quite there yet. Maybe we need more varied embodiments in the data set. Maybe we need to improve our models. And if we get there, then of course, evaluation will be easier. So where does that get us? We can train models on data from many different robots. These models are better than specialized models. These models can be fine-tuned to new embodiments, but there's still things lacking. Like the zero-shot stuff isn't quite there yet, and there's more work to do. So what does this mean for benchmarking? Well, it means that you can download a robotic foundation model, like a VLA, and fine-tune it to your robot. Like you can do that today. You can download Pi0, you can download other models, you can download like NVIDIA's model and so on. And you can develop a new model trained on the same cross-embodiment data set and fine-tune it to your robot. So that's pretty cool. So what does this mean for evaluation? Remember that benchmarking in robotics is hard because everyone has a different setup, so there are a few options. Option one is fine-tune and test. So you develop a new model, train it on the cross-embodiment data set. That's the data set everybody has. You download baseline models that were trained on the same data set because that data set is public, and then you fine-tune both your model and the baseline models to your particular evaluation setup because your evaluation setup is probably not the same as something in the data set. So that has some pros and cons. It's good because everyone uses the same pre-training data set, so the pre-training doesn't unfairly advantage your environment. But it's bad because everyone gets to set up their own tasks, so you can set up a task that fits like the inductive bias of your model better. And that will happen, so you kind of have to keep yourself honest. And you get to fine-tune everyone else's models, and you probably won't fine-tune them quite as well as the original authors did, so there's like a little bit of a know your method sort of confounder here. But still better than the totally balkanized setup. Another option is to set up similar setups. So develop a new model, train on a standard cross-embodiment data set, download baseline models, set up an embodiment that is present in the cross-embodiment data set, and then test. So that's good because everyone uses the same pre-training data set, and you don't get to make your model better by just giving it like special data, since you don't get to add data at all. But it's bad because someone needs to actually like make this shared setup, and it needs to be broad and diverse enough that other people can set it up, and it limits research on producing cool new tasks, embodiments, and setups, so it limits that silver lining I mentioned before. So there's disadvantages to this. Option three is zero-shot generalization. So if we figure out how to do zero-shot generalization to new embodiments, then you can develop a new model, train on a standard cross-embodiment data set, download the baseline models, test them in zero-shot on your robot, and then you can also fine-tune them to your setup and make them even better, so you can report both conditions, and then add your data set to the global shared data set, so that next time around your cool new task can be used by everybody else. So that's really good because everyone can use the same pre-training data set. You can have this fair comparison, you can also have the unfair comparison, you can show them both side by side, you can still innovate on the setup, but we need to solve some open problems to make this happen. So good to do research on cross-embodiment robotic models because then you can have better evaluation in the future. Early steps towards this, one thing I want to mention is the Droid data set. This is a standardized setup that if you're working on large-scale robotic learning, you can download and use. It's using a Franca and a Robotique gripper. It's collected in lots of different environments, so it facilitates generalization to new environments. And initially when this data set was collected, it was actually very hard to get one model that worked across the board on all the Droid setups. But since then, actually, robotic learning technology has advanced, and we can actually train a single model that will generalize to lots of different environments. This is a robot running at University of Washington, another one at NYU, another one at Berkeley, running the same model in environments that were not in the data set, but tasks that are qualitatively similar. But this comes at the cost of the task being kind of simple, so it's good for iterating on algorithms and models, but maybe not so good for demonstrating a really cool task. So, because innovating on tasks is good too. Another project, and Carl will talk about this, called RoboArena. This is an approach to really embrace the AB eval framework. It's like similar kind of A/B evals that were proposed for LLMs, where you can actually submit your droid, in this case trained policy, to a global evaluation network where other people can take your model and run it head-to-head with their own models and estimate kind of like an ELO score, as long as your model will work across the board on these setups. And if everyone trains on the same setup, on the same data set, then even though the test setups will vary in difficulty, the head-to-head competitions will allow you to calibrate the strength of your model. So I won't go into this in too much detail because Carl will talk about this a lot more, but the good thing is that this allows robotic foundation model researchers to compare models without even setting up robots, because you can submit it to this global evaluation network. The downside is that it requires community buy-in to actually set up evaluation stations, and so far there are a couple of universities that are doing this, but not that many. So some closing thoughts. I would say when it comes to benchmarking in robotics, let's not be perfectionists. Benchmarks are local surrogate functions, and they're good insofar as you can make progress. Even a benchmark that you only use in one paper that you write yourself is still a surrogate function if you do it right and you keep yourself honest. So let's not be too hard on yourselves. As robots get better, benchmarking will get easier because systems will generalize more broadly. So if it's tough now, it's going to get better. And my own personal, highly biased opinion is I think that cross-embodiment learning, in the world of robotic learning in particular, is something that will make a difference in making benchmarking more accessible. Thank you very much.
All right, thank you. Questions on this?
Where do you think are the boundaries of cross-embodiment where you can really have a benefit? Right now, most of the robots are similar kinematic chains, a pin creeper.
Yeah. That's a really good question. I think it's the complexity here is that it probably really depends entirely on the data sets. So if we had like thousands of different types of robots with different kinematic chains, then we could do a lot of research on generalizing across different kinematic chains and everything would be wonderful. But of course, the number of different types of robots is like in the tens, not in the thousands. So partly it's kind of out of necessity that you're gonna have to draw the boundary somewhere. Now, I will say that in terms of like very controlled scientific experiments, you can show like some pretty remarkable degrees of transfer. So we had an experiment with Chelsea Finn and Dorsey Siddique's group at Stanford where we showed that navigation data could actually help with manipulation. And it kind of makes sense because with navigation data, you kind of learn basic visual servoing behaviors, and navigation data is very diverse, so it makes sense that it would also help with manipulation insofar as manipulation involves visual servoing. But these are, of course, like very like tightly controlled setups. So lots of open questions there, and those open questions are very confounded by availability of diverse multi-robot data.
Yeah. So you briefly spoke about RoboArena as one solution to give you sort of A/B evals, right? But what do you think is left for something like this to be way more scaled? One thing you mentioned is just everybody needs to have the identical setup, which is like potentially a very expensive robot with very expensive gripper and cameras and everything. But you also mentioned things like you need human evaluators at all times. So along these 2 points, what else do you need to scale it up so that every lab can do
Yep, this is a really good question. So one thing I want to clarify is I don't think that everybody needs the same high-end setup. I think if we have good cross-embodiment data sets, the test setups just need to be in distribution. And the broader the cross-embodiment data is, the more variability the system can accommodate in terms of eval setups. And this is something that if we organize it well as a community, it can grow itself, right? So maybe someone comes out with like a new robot and it's really good and everyone starts using it. If data from that robot gets contributed back to the cross-embodiment data set, then it can start getting incorporated into the evaluation network. So this is something that I'm sure Carl will talk about a lot more, but it's with cross-embodiment data sets, I think it's possible for this A/B setup to actually be very scalable. And in particular, since models are always compared head-to-head, it's okay if some of the setups are a lot harder than others. As long as you compare the model enough on enough setups, you will get a calibrated score of its capability.
And what about the scalability part, like other aspects beyond just having the setup to make it?
Well, yeah, so I think like the big challenge with any kind of community-driven thing like that is that someone has to like do these things. So I could imagine all sorts of ways this could work in the future. If the idea takes on, you could imagine that maybe people will if you're a robotic learning researcher and you want to participate in this, maybe you get like some amount of evaluation credits for every eval you run. So if you run an eval, then you can run your model on other people's evals. But there has to be some amount of, I guess, cohesion, coordination, and willingness to contribute to the greater whole.
Yes. So when it comes to this question of keeping yourself honest for your own local surrogate function, one of the things I remember my advisor telling me like my first year is you're looking for something that other people can't do And so, they can't do this task, okay, or whatever. I'm now gonna target that, I'm gonna make my thing, it's gonna work on that task. Hey, by design, everybody else's doesn't. Have I made progress? Like, how do we tackle the need to be looking at the new, the novel that other people can't do, and yet still be keeping ourselves honest in terms of all the other things that...
I mean, that's a very fair point. But I will say, like, I think on the positive side, I think that is one of the strengths of the somewhat hokey, like, robotics evaluation procedures, that because we all set up our own tests, we do get to experiment a lot more with that, and we can set up some, like, cool new thing that wouldn't have been possible with prior methods, and that's actually, like, a very acceptable thing to do. In fields that have implemented benchmarks, this kind of innovation is extremely difficult. Because people will not pay attention to work that evaluates on tasks that are not broadly accepted benchmarks. So there's a balance to be struck, and I think that balance probably involves being particularly careful in how the prior methods are set up, being particularly careful in like not introducing unnecessary variability just for the sake of like teasing out the difference in the method. But the point I want to make is that it's not unequivocally bad. Like there's a really good thing there.
I'm not disagreeing with that. It's more like how do I, as a researcher, or suggestions to my students, guide them to make sure we're not making mistakes of dishonesty?
Yeah. It's a really good question. I don't think I have like the perfect answer for you. I think one thing I would say very constructively and kind of forward-looking is, I think instead of worrying so much about like the past, facilitate the progress in the future. So what I would do if I'm setting up some like new task and like every prior method fails, I would make sure that task is then more accessible to others in the future. Because then if I like messed up and I like made my method look unfairly good, well, if everyone else can like go and try similar things, then they'll probably show that my method was good. And what's actually keeping me honest is not the pressure from the papers from the past complaining to me, but the fear of disapproval in the future from other people that take my method and show that it sucks.
Maybe that's something we can talk about in the breakouts or something, then, is how to take these one-off bespoke things or bring them back in.
Yeah. And that's definitely hard. But I do think that when we set up these experiments, if we just keep in mind that we would like want to set up these experiments to be a demo, but also something that we want other people to try, there are often kind of low-hanging fruit that we can take advantage of that will make it easier for others to access.
All right, let's thank our speaker. And so.